All right, looks like I'm the only person in Zoom right now, but just in case, if you're here on Zoom, please type something into the chat so I can get your name for the roll. All right. Hopefully you guys can see what I have going on here on the board. Over on the right-hand side here, I have a simple comparator circuit. And on the left-hand side, I have drawn my various voltage sources in LT Spice. I choose to do this methodology to keep my actual circuit of interest a little bit neater. So maybe I should explain what I'm doing. So let me see if you guys can see my mouse type thing. Yeah, okay. So what I've done for my power supply voltages is I have just placed two voltage sources on top of each other, tied them together, and put the middle terminal as ground. So what I can do there is then I can use this topmost, the positive polarity voltage of my topmost source to be my positive power supply voltage, and this one down here to be my negative supply voltage. And what that enables me to do is, using those labels, I can then place the same label on my op-amp circuit, and it automatically applies those voltages so that my actual op-amp circuit isn't crazy busy with voltage sources and all that crap applied at every terminal. Over here, I have my input signal, and then I also have included a noise signal. That's just to demonstrate something. And then finally, this fifth voltage source is a reference voltage, which you can't see it, but it's giving 2 volts. So with that in mind, if I run a simulation of this circuit, and I'm going to click on VN1 and VOUT1. Let me move this dumb thing out of the way. We can see that I have a comparator wherein every time my input voltage exceeds 2 volts, my reference voltage, my output goes to VCC plus, which is 10 volts. And every time my input voltage goes below 2 volts, my output goes to VCC minus. So this is a simple non-inverting comparator. Now I'm going to break it by including noise on my input signal. It's going to take it a minute to do all the simulation stuff because it's collecting many, many, many more data points. All right, so it looks relatively the same, except that those vertical regions look a lot thicker. So what I'm going to do is I'm going to zoom in real quick here. So I'm going to change this from, let's see, let's make this guy 0.1. And make this guy 10. And I think that should capture it. Yeah. So this is me looking at what's going on when my input voltage signal is noisy, but it's around the trigger level or the reference voltage, as my output voltage swings wildly from VCC plus to VCC minus, which in some applications may be perfectly okay, and in other applications may be very, very bad, okay? So to combat this, we are going to employ what's called a Schmitt trigger. And a Schmitt trigger is nothing more than a comparator that uses a positive feedback loop to cause latching to occur. So I'm going to change my reference voltage real quick to 0. And I'm going to look at, let me delete this graph. Run my simulation again, just real quick. So I'm going to look here at is my comparator. over on this side, VN2 is my noisy voltage, input voltage. Vout2 is the output of my Schmitt trigger. And I can see that I now get the regular comparator output like I would expect. I don't have those random fluctuations where it's swinging from VCC plus down to VCC minus, thousands of times in a fraction of a second. But I do have a trade-off here, okay? So we can see that my output, it looks like it is going high. Right now, my reference voltage is 0 volts. My output is not going high when I see 0 volts. It's actually going high when I see +1, and I'll show you that for sure in a second. Also, my output is now going low when it gets to -1. So I can add a trace. I'm just going to do 1 volt. And let me add another trace of -1 volt. And we can see that that is exactly where the switching is occurring. These values, 1 volt and -1 volt, are what are called so 1 volt is the lower trigger limit. And that is, excuse me, 1 volt is the upper trigger limit. And that is the voltage at which, when our input exceeds that, the output swings from low, VCC minus, to high, VCC plus, and then -1 volt is our lower trigger limit, where our output voltage swings from VCC plus, high, down to VCC minus, low. Those upper trigger limit and lower trigger limits are simply a function of this resistor network right here applied in our positive feedback loop. So we're going to take a few minutes to mathematically go through and figure out what's going on and develop some expressions to figure out how we can design circuits for specific upper and lower trigger limits. One other thing that I want to do real quick here, just because it's pertaining to homework 2, which I think is due soon, like Friday maybe or something like that. Let me run another simulation here. Oh, wait, actually, let me kill this. I want to look at my simple comparator because I believe you guys have a comparator homework problem. I'm going to put VN1 on. The reference value was 2, right, for your homework problem? So let me run the simulation. Here I have VN1, Vout, everything looks hunky-dory. This is not the graph that I'm asking you to give me in LT Spice. What I want is Vout versus Vn. So to change my dependent variable, if I right-click on the x-axis, I can literally type that instead of plotting this versus time, I want it plotted versus the voltage at Vn1. And in doing so, let me get rid of VN1. We have the exact same type of graphs that we wound up drawing in class, which is what I want for the homework assignment. So all I did, mouse over this region, right click it, and change the variable on my x-axis. And that takes care of everything. And we'll do that with the Schmitt triggers momentarily too, to see something interesting about that. All right, so let's take a look at this non-inverting Schmitt trigger circuit. Right. So for a non-inverting Schmitt trigger, we start with our simple op amp. Positive here, negative here. We are going to apply our reference voltage to our inverting input terminal. We're going to take our output at the output terminal, but we're going to do something very, very important here. We are going to be applying positive feedback by placing a conduction path, in this case containing a resistor, which I'm going to call R2, between the non-inverting input terminal and the output terminal. So we have feedback anytime there is a path between the input and the output. And it's positive feedback when it's connected to the positive terminal. It's negative feedback when it's connected to the negative terminal. Positive feedback is an unstable form of feedback. Let me finish this guy real quick and then I'll talk about that more in a second. Here's my resistor R1. Here is where I'm applying my input. And then I obviously have my power supply VCC plus and power supply VCC minus as well. All right, so positive feedback. How many of you have ever been at an assembly or something like that when somebody's been talking into a microphone and heard some high-pitched squealing? Or been to a concert and saw the guitar player walk up in front of his amplifier and place his guitar strings towards it and it starts squealing real loud? That is an example of positive feedback. If you're speaking into a microphone, your voice is comprised of a pressure wave, right? You speak, a pressure wave occurs, hits a very thin film transducer in the microwave, which generates a voltage signal. That voltage signal gets carried down to the amplifier, which is amplified and then output through the speakers. Well, the speakers create sound through a pressure wave as well. If that microphone picks up the speakers too, that's creating a positive feedback loop where it's building on itself over and over and over again. So the noise of the speakers gets amplified, goes in the microphone, gets amplified, goes to the microphone, gets amplified, etc. That is a positive feedback loop, and that is exactly what's occurring here. In a negative feedback loop, which is what we're going to talk about on Friday, we're taking a little bit of the output away with every cycle, and it gives us very, very stable systems. So we're able to bring the voltage gain. So the voltage gain of this system is effectively the exact same thing as the open loop voltage gain. It just takes it a minute to get there. So somewhere on the order of hundreds of thousands. For negative feedback amplifiers, we can bring that gain down to single digits or a couple of hundred or really whatever we want. It's a lot easier to control. All right, so that's enough about positive feedback out of me. Let's figure out how this darn thing works. So the first thing that I'm going to do is I'm going to have to draw a practical model representation of this guy, okay? So I'm going to start with just my op amp circuit. So I have some finite resistance Rin. This node right here is my non-inverting input terminal. This node down here is my inverting input terminal. So this voltage drop over my input resistance is my differential voltage VD. And then over here, I have AVOL multiplied by VD. And here's my resistor R out. And then this guy right here is my ground, such that this voltage drop between this node and ground is my output voltage. So that's just a simple model for my op amp by itself. Between the inverting terminal and ground, I have my voltage V reference. Between my non-inverting input terminal and ground, I have my resistance R1 in series with my voltage Vn. And I have feedback from my inverting input terminal here to my output terminal here, comprised of resistor R2. This circuit is going to be a little bit difficult to analyze, so we're going to make two important assumptions. One is that our input resistance of our op amp Rn is much, much greater than our biasing resistors R1 and R2. So we would use, say, kilo ohm size resistors for R1 and R2 because we know that our input resistance should be somewhere on the order of a mega ohm or larger, which is exactly what we talked about in the last class. We're also going to assume that our output resistance R out is much less than R1 and R2. Again, these are the exact same assumptions that we talked about with regards to sizing resistors last class. So we're not doing anything new here. This is going to make the math a little bit easier. So what I'm going to do is apply Kirchhoff's current law at my non-inverting input. So I'm going to be adding this current, and this current together. So my current directed to the left through resistor R1 is just V plus minus Vn divided by R1. My current directed through my feedback resistor is V plus, minus V out over R2. And lastly, I will have V plus minus V ref, which is the voltage present at my inverting input terminal, divided by Rn is equal to 0. Right, just good old Kirchhoff's current law applied at that non-inverting input terminal. Now, if we apply our first assumption that Rn is much, much greater than R1 and R2, what can we say about our third current term in our KCL expression? It's essentially 0, okay? So we're going to throw this guy away because it's not really doing much of anything. And that is also going to bring us to something else that's very important here, okay? If the current flowing through resistor Rn is effectively 0, that means that our voltage present at our non-inverting input terminal is the same as the voltage present at our inverting input terminal, which means V plus is approximately equal to V ref. Okay? So if I make that substitution, V ref minus Vn over R1 plus V ref minus V out over R2 is equal to 0. And I do a little bit of algebra. So I could say that Vref over R1 plus Vref over R2 is equal to Vn over R2 plus V out, sorry, Vn over R1, I apologize, over R2. This is the same as Vref times 1 over R1 plus 1 over R2, which is just R1 and R2 in parallel, the inverse of R1 and R2 in parallel. So that's going to look like R1 plus R2 over R1 multiplied by R2 is equal to Vn over R1 plus V out over R2, which finally leads me to Vref is equal to Vn times R2 over R1 plus R2 plus V out times R1 over R1 R2. So this equation actually tells us everything about how this circuit behaves. The reason why this one equation does everything is because we know that because this is a positive feedback circuit, our output voltage is always going to be either our positive supply voltage or our negative supply voltage, right? It can't be any value in between for more than a fraction of a second. It's always going to settle to VCC plus or settle to VCC minus. So from this, we can determine our trigger levels. So get our, yeah, okay. To get our upper trigger level, which is defined as the voltage at which our output changes from low to high, we simply solve that circuit for V in when V out is equal to VCC minus. And to get our lower trigger limit, that's the voltage at which our output swings from VCC plus down to VCC minus. So it starts at VCC plus. We say that V out has to be equal to VCC plus, and then we solve for our voltage to get. That's it. So if we look at my SPICE diagram here, assuming our reference voltage was 0, we observed that we had an upper trigger limit of 1 volt and a lower trigger limit of -1 volt. And we can prove that by simply subbing in these two resistor values, right? So what I'm saying is we take our original circuit, original equation, Vref is equal to Vn times R2 over R1 plus R2 plus V out times R1 over R1 plus R2. Our upper trigger limit then is going to be Vref, which was 0 volts, is equal to Vn, which is what we're solving for, times R2, in this case 90 kiloohms, divided by R1 plus R2. 90 plus 10 is 100, so it's just going to look like 9/10, the ratios, plus V out, which in this case, VCC minus is -10 volts. And then we have R1 over R1 plus R2, which is 1/10. So we have, let's see, let's do a little bit of math here. So this looks like -1. So we add 1 to both sides. So 1 is equal to Vn times 9/10. So Vn is 10/9. So it should be our upper trigger limit was around 1.1 volt, which is what we observed. It was somewhere really close to 1. For our lower trigger limit, we have 0 volts is equal to Vn times 9/10 plus +10, because we're at VCC plus now, times 1/10. So this looks like 1. So we have -1 is equal to Vn times 9/10. So -10/9 is our lower trigger limit. So somewhere pretty close to -1 volt as well. So our derivation matches what we had observed with our simulation. All pretty straightforward. Again, this latching, having a upper trigger limit and a lower trigger limit, that's what's causing this thing not to ring or oscillate when we observe a noisy signal. So let's look at a inverting Schmitt trigger. Okay. Oh, that's too many pages. So for an inverting Schmitt trigger, we are going to have something like this. So we're still going to have our positive feedback. Here's resistor R2, VCC plus, VCC minus. Here's our resistor R1. And now we are going to place Vref at that leg of resistor R1, and we're going to apply Vin directly to our inverting input terminal. We could go through the motions of redrawing this circuit using the practical op-amp model and all that kind of jibber jabber. But what is the fundamental difference between this circuit and the non-inverting Schmitt trigger? Yeah, so Vn is where Vref was, and Vref is where Vn was. So I would argue that we can just take our original equation and transpose Vn and Vref and get exactly how this thing behaves, right? So the fundamental characteristic equation for this guy is Vn is equal to Vref times R2 over R1 plus R2 plus V out multiplied by R1 over R1 plus R2. And the upper and lower trigger limits are defined in the exact same way. Upper trigger limit, we put V out equal to VCC minus. Lower trigger limit, we put V out is equal to VCC plus, and then solve for V in, which in this case is even easier because it's already isolated to one side of the equal sign. So this is a inverting Schmitt trigger. We've talked about a non-inverting Schmitt trigger. This is 2 of our 3 positive feedback circuits. The last positive feedback circuit that we are going to talk about is the op-amp multivibrator. All right. This guy has a lot going on. That's the wrong color. Hold on just a second. I'm going to have to save this, close it, and then reopen it, or I'm going to continue to get that little error message over and over again. So our circuit, again, this guy is a bit difficult. Actually contains both positive and negative feedback. I'm going to put my ground reference here at the bottom left-hand corner. Which means this node is the voltage drop over my capacitor. And I'm going to call this node right here my reference voltage. So there's something very fundamentally different about this circuit than any of the ones that we have dealt with to this point. Anybody recognize what that is? There's a capacitor. Okay, sure, that's one fundamental difference. 2 feedback loops. All right, there is positive feedback through resistor R1 and negative feedback through resistor R. But there's one other thing that's obvious, but you're missing it. Yes, sir. There is no input voltage. Exactly right. Okay. There is no input voltage at all. What this guy does is it uses the energy stored in the capacitor to create an oscillating output voltage waveform. Okay. So let's start by assuming that our capacitor voltage is equal to 0 and our output voltage V out is equal to VCC plus as effectively initial conditions for this system. Okay. Because it has positive feedback, the output is always going to be either VCC plus or VCC minus. The negative feedback can't take it away fast enough to change that. So when V out is equal to VCC plus, V reference has a positive value, right? Because there's simply a voltage divider circuit between V out and ground, and V reference is that voltage in the middle, right? If no current can branch off, then V ref is just the voltage drop over R2, which is just going to be V out times R2 over R1 plus R2. Simple voltage divider. If V out is positive, V ref is positive, okay? So along the other direction, we started off saying that the voltage drop over the capacitor started as 0 volts. If V out is positive, that means there is a voltage drop over that resistor R, which means current must be flowing through it, right? That current can't branch off and flow into the inverting input terminal. So what it's going to do, excuse me, is it's going to wind up charging this capacitor C. So as current flows into the capacitor terminal, the voltage drop over the capacitor is going to get larger and larger and larger. So graphically, what's going on, let's see. So let's start with our output voltage, which I'll draw over here, starts as VCC plus, which means our reference voltage, let's start it right here, is going to be, I'm just going to call this Vref. This is going to be V out. And our capacitor voltage, let's see what color I want to do it in. Blue. It's going to start gradually growing towards hitting Vref. And it's going to take time to do that because this is an RC circuit, right? So it's not going to instantaneously jump up there. It's going to follow the time constant, R times C, and it's going to take that long for it to charge or whatever, or actually 5 time constants or whatever to get close to charging. But the rate at which it charges is based on the time constant. When that capacitor voltage finally meets V reference, and technically exceeds it, right? So if VC gets higher than V ref, V out falls to VCC minus, right? So we have, if VC is ever greater than this voltage, then we have the trigger condition to make the output fall to the other side, all right? So V out falls down, and it's just going to cycle back and forth between VCC plus and VCC minus, like so, where this is the period of oscillations that is generated. Our reference voltage is going to follow the exact same pattern, but it's just going to be a fraction of V out and VC, which I'm drawing in blue, is going to slowly discharge and then charge and then discharge and then charge over and over and over again. That's what our voltage waveforms should look like. The time it takes for this to occur, or the period, T, is equal to 2 times R times C times the natural log of 1 plus beta divided by 1 minus beta, where beta is the ratio of the resistances, R2 over R1 plus R2. So another thing that we can know is that the frequency at which these oscillations are occurring is 1 over T. By definition, that's something you guys learned back in engineering 121, I believe. So we can adjust the values of either R, C, or R1 and R2 to be able to generate from purely DC sources an AC signal with a specific frequency. So this is how we can make clocks and things like that. Or if you're a guitar pedal dork like I am, this is how you can make a tremolo circuit, causing the voltage, you can light up a LED at specific intervals and then use a photodiode to translate that into turning your voltage on and off, which is exactly what a tremolo unit does for a guitar effects processor. So you can use this stuff for lots of neat and nifty little things. So I have built one in LT Spice. Let me close this out. Open A-stable multi-vibrator. And let me find my keyboard here because I'm going to have to change a couple of things. All right. So right now, this guy is using the universal op amp, which is the one that I prefer to use. I don't know if I've mentioned that to this point, but whenever I draw an op amp, excuse me, in a LT Spice circuit for this class, I always use the model Universal Op Amp 2. So let me just show you real quick here. If you type in UNI, it brings up Universal Op Amp 2. I like that one a whole heck of a lot because if I right click on it, I have a list of editable parameters. So I can change the open loop voltage gain. Right now it's set to 1 million. I can change the gain bandwidth product, which means absolutely nothing to you guys, the slew rate, which means nothing to you guys, but I can change the input resistance, all that kind of good stuff too. So I can use this one to do an awful lot of things. And I can also change the spice level. So right now, level 2 treats this as an ideal op amp, except that saturation distortion is taken into account, meaning the output can never exceed the power supply voltages, which is how we're doing practically all of these problems. Level 1 treats it as an ideal op amp where the output can be anything it needs to be. There is no restriction on saturation distortion. So if I run my simulation here and I look at my output signal, let's plot VC, VREF, and Vout. Everything is 0, okay? The reason that it's treating everything as 0 is because this is an ideal op amp. There's no energy put into anything, it can never start actually vibrating or oscillating. So if I change my initial condition on my capacitor voltage from 0 volts to 1 millivolt, that is enough energy to make it start doing exactly what it's supposed to do in a couple of seconds. If I jump this up to 1 volt, it effectively comes out of the gate doing exactly what it needs to be. So to make this simulation work, I effectively just had to put a little bit of energy stored in the capacitor, and then it starts to build and build and build as it oscillates back and forth until it goes full swing and does exactly what I told you it was going to do. So there is a brief problem on the homework cassette for today's stuff that'll be about determining the range of frequencies that you can get out of one of these for specific values, but that's about as in-depth as we're going to get on this guy because it's kind of beyond the scope of this class, to be honest. This is only the second quarter I've ever taught this particular circuit. So we're finished 30 minutes early again. I'm sorry. Friday will probably actually run the whole time, where we get into negative feedback op amp circuits. So Friday is negative feedback op amp circuits, starting with non-ideal, moving towards the ideal op amp. Monday will be effectively a review of circuits 1 material, wherein we talk about common ideal op amp topology, so non-inverting amplifiers, inverting amplifiers, inverting summers, differencing amplifiers, integrators, differentiators, and then we'll finish up op amps 1 week from today with cascaded op amp circuits, which is when we chain multiple op amps together. All right, so don't seem to have the roll sheet in front of me. Oh, is that it right there? All right, thank you. So I'll see you guys on Friday. Have a good rest of your day.